Okay, so I just want to spend a little bit of time talking about something called as dynamic light scattering technique. Again, in this you have a way of extracting the particle diffusivity, okay, and from that you can get the size of the particle. Okay. Yeah, any thoughts? What do you know anything about Brownian motion? Sorry, anything about dynamic light scattering? What is it? Any basics of scattering? No. Okay, let's. Okay, all of you may know this, right? What is this?
Scattering of light.
Yeah, this is a laser show, right? I mean, very popular, right? And why do you get this fascinating beam of light? Why do you think you get these things?
Because of refraction of light. I mean, all the lights travel at different colors travel at different speed.
This is nothing to do with the color of light. I don't know if you have gone to any laser show. You will see that they make something, right? I mean, if you have clean air, you won't get this. Yeah, right. They create some synthetic particles, right? Some fog or smoke like thing or something like that, right? Only then you see this, right? Yes, right. So so in that case, you can think about this liquid in air dispersions, okay, or particle in air dispersions, right? We talked about this, right? There are different classification of dispersions. One of the dispersions are, if you have a dispersed species, could be liquid or a solid particle, and that's in air, right? So in something like a laser show, your continuous medium is the ambient air, and they have created some particles, okay, which essentially scatter light. Okay. Now, okay, so the origin of scattering, right? So any kind of scattering, okay, is due to what is called a localized non-uniformities in the sample. Okay, it becomes clear from the previous example, right? If I had only air, clean air, then you won't see these colors, right? So you need to have a localized non-uniformities. Okay, in this case, what do I mean by that is you should have maybe air with some particles, okay, or liquid some particles, right? That's okay. The particles in that case constitute non-uniformities in the sample. Okay. Now, people use different light sources in experiments. Okay, you can use a visible light, okay, or white light, right, or you can use X-rays, okay, you can use lasers, you can use neutrons, okay, and depending upon the light source that you use, okay, the scattering is kind of attributed to different reasons. Okay. If you use visible light, okay, then the scattering originates from the refractive index variations. Okay. I have a particle that has some refractive index n1, a fluid medium that has some refractive index n2. Okay. Only when you have the refractive index difference is when you will have scattering. Okay. So now, what I mean by that is if I want to do a dynamic light scattering measurements, okay, if you have a fluid which has a refractive index n1, if I have dispersed species whose refractive index is very close to that of the medium itself, then you can't do scattering experiments. Okay. The same thing is true for microscopy as well. When you are doing microscopy experiments, if I have a solution, okay, and you can do these experiments. Okay. People do what is called as refractive index matching, right. That means there are some classic videos in YouTube, you can look it up. Okay. I have a container, I have glass, this say a beaker, right, and there is a glass slide. Okay. Now, when there is nothing in the container, because there is enough refractive index difference between the glass and the ambient air, which is right, you can see the glass rod, right. Now, what you do is you put water, you can still see the glass rod, because there is again a refractive index difference between your water and the rod, right. Now, if I replace this with fluid, maybe up to this level, and and if that fluid has same refractive index, the only thing that you will see is what is above. Okay, that immersed portion you won't be able to see. Okay, so therefore, depending upon in scattering, okay, the scattering originates from either the refractive index difference, or if you use X-rays, what is important is the spatial fluctuations in the electron density within the material. Okay, that is what gives rise to scattering when you use X-rays. Okay. Similarly, when you use neutrons, people talk about what is called as a scattering length density difference. Okay. So, you can read up a little bit about this when you go back. The idea is there has to be some heterogeneities or non-uniformities, some difference in particular properties, and that is when you can carry out scattering experiments. So, these are typical wavelengths, right. If you use laser light, typical wavelength of the laser light is about it will be depending upon whether you use blue laser, red laser. Okay, your wavelength would vary, but typically you can say is about 500 nanometer. If you use X-ray scattering, okay, this wavelength is smaller. Okay. If you use again neutron scattering, again the wavelengths are much smaller. So, depending upon the wavelength that of the light that people use, that will give you the length scale that you can obtain from scattering measurements. Okay. And that length scale is kind of expressed as some parameter, again not important at this point, which is expressed as nanometer inverse, and 2 pi by this parameter, okay, S will give you the length scale that you can obtain from the scattering experiments. Okay. Let us think about it. Okay. So, 2 pi divided by is 10 power minus 3 to 4 into 10 power minus 2, right. Therefore, the length scale that I can get from scattering experiment when I use a laser light, it is 2 pi into 10 power 3 to 2 pi into or 0.5 pi into 10 power 2, right. Okay. That is in nanometer. Okay. Now, let us do the same thing for this one. Okay. So, these numbers are smaller, right. If I look at 2 pi divided by these numbers are smaller, right, compared to these numbers. Okay. That means, if I want to measure size of smaller things, okay, if I want to measure the size of smaller things, okay, I should use the light source whose wavelength is smaller. Okay. That is all I wanted to say. Okay. Now, okay, this is a there are different types of scattering experiment that people do. We won't introduce these terms, but maybe what I will do is I will come back here. Okay. People do different kind of scattering experiments. One is what is called as a static light scattering experiment. Other one is what is called as a dynamic light scattering. Okay. In static light scattering, what is measured is the time average okay, time average intensity of the scattered light, okay, is what is measured. Okay. A typical experiment looks something like this. I have a light source, okay, and I have a sample, and this light beam is incident on the sample, okay, and the local heterogeneities, right, or the non-uniformities in the sample will make the light deviate or scatter light, and that is actually collected on a screen. Okay. And this screen is typically a camera. Okay. What you record is something called as a pattern like this. Okay. This is what is called as a scattering pattern. Okay. And what you see here is related to what is the microstructure of the sample, or in other words, what is the spatial arrangement of particles in the fluid. Okay. What you are seeing here is a case where particles have formed chain, right. Now, if you have a case where the particles have formed chains, you will get a scattering pattern which is kind of elongated in a particular direction. Or this is an optical microscopy image, okay, where the particles are nicely arranged, right. Everything is a hexagonal pattern, right. Right, it's a hexagonal pattern. Now, this is a microscopy image, okay, by an optical microscope. We have taken that, converted that into a FFT pattern, and what you again see is a hexagonal pattern, right. Can you see here? Okay. In a way, one way to think about this static light scattering experiment would be, I am imaging microstructure, but not in the real space, in what is called as a Fourier space. Okay, that's all that is there. Okay. So, therefore, in a typical static light scattering experiment, what you do is you measure time average intensity of the scattered light, okay, and it is measured by fixing your screen or a camera at a particular location, okay, and depending upon the location of that, okay, whether it is very close to the beam, very close to the sample, or very far away from the sample, okay, this theta will vary, right. Depending upon the theta, the variation of the theta, you can essentially obtain information about different length scale, okay, present in your system. Okay, let me put it at that, in that way at this point. Okay. Now, yeah, so that's something about static light scattering. Okay. In the dynamic light scattering, what you do is, what you measure is a fluctuations in the light intensity as a function of time is measured. In one case, you measure a time average intensity, that is in static light scattering. In the dynamic light scattering, what you measure is a fluctuation in the light intensity itself as a function of time. Okay. That is the difference between the static light scattering and the dynamic light scattering. Okay. The instrument for dynamic light scattering, it looks something like this. This is one of the tabletop devices that is available, and you can actually use this for a measurement of size of the particle, okay, or polymers, or some surfactant structures. I talked about this liposomes, right, or vesicles. You can measure size of that. You can also use such an instrument for measuring charge on the particle, molecular weight of polymers. There is a lot of, okay. within the instrument, what essentially there is a laser source, there are a set of lenses, and these lenses, as I said, are useful in sending a collimated light, right. Okay. And it falls under the sample, okay. And there is a detector. Okay. Typically these detectors, what they do is they are what are called as photon detectors. Okay. They essentially measure the number of photons, okay, scattered. Okay. And that is your sample that has some particles. Okay. Again, I had mentioned about the scattering volume at some point. The intersection between the incident beam, this is your incident beam, right, and the scattered beam, okay, that gives you some finite volume, right, and that contains the particle that you have in the fluid. Therefore, the scattering volume contains, okay, a much larger, I mentioned this point, right. If you look at the scattering volume, so even if it is like say of the order of say millimeter cube volume, okay, that millimeter cube volume will have really large number of particles. Okay, even if you take 0.001 weight percentage sample, it turns out that number of particles in 1 ml would be as high as 10 power 12 to 10 power 14 particles. Okay, therefore, the scattering volume really contains a large number of particles than what can be analyzed by something like microscopy, where you look at only a small section of your sample. Okay, for example, something like this, right. If I am going to analyze particle size from this, okay, of course, they look monodispersed, but then I will be limited to maybe few hundreds of particles, right. However, if you do scattering experiments, the scattering volume will contain essentially large number of particles. Okay, therefore, you get a better average for the particle size when you do DLS experiments. Maybe I will stop here. We will continue with talking about how does one use DLS for measuring particle size. Plus, we will also talk a little bit about using Brownian motion for looking at what is called as a sol gel transition. Okay, that is what we will try and do in the next class. Yeah. Thanks.